All right, in this video, I'll be going through a paper 2 question related to wave physics. The question reads, for a progressive wave, state what is meant by the wavelength and then the amplitude. So these are just definitions, which is why they're only a single mark. This is something that you're either going to know it and earn the mark, or you're not going to know it and you probably won't earn the mark. Don't count on you being clever enough to like just kind of BS your way through something that's very precise, like the definitions of physics. Like I can kind of know what that is. You want to have the precise textbook definition. The wavelength is the length of the wave. So it's the distance between, it's kind of like two adjacent identical points on the wave, like after it repeats. So I like to just say the distance between, like from crest to crest, because a crest is an easily identifiable point. And you can see the next crest, right, the point of displacement, amplitude, but it could really be any point. So remember we said like if the wave starts here and where it repeats, the next identical point is like that one. So the wavelength is the distance here to here. But if the wave is continuing to oscillate, then we say, oh, from crest to crest, that's the wavelength, or from trough to trough. So the distance between adjacent identical points on the wave. One way to kind of word it, if that sort of makes sense to you. Distance between and I'll put in parentheses, i.e. crest to crest. All right, remove any doubt that I'm talking about. But you don't have to define the wavelength as crest to crest, because trough to trough, or this point to this point, it's like any identical sort of, once the phase of the wave repeats, right? It's like this point and this point have 0 degrees of phase difference, or 360 degrees of phase, right? So as soon as you get 360 degrees away from the point, then the distance between those points is the wavelength, okay? And that may be another way to sort of define it. And that again, it's a human being that's reading the definition. And if you define it something like that, that you really know it, and you use 360 degrees of phase, 2 points that are 360 degrees of phase separate from each other, the examiner is going to know, okay? But just be careful to not say anything incorrect. You don't want to, what we say, Monte Carlo the whole thing and just throw all the physics you know at it. Give the definition of frequency, period, wavelength, intensity, give them all. Because one of those answers got to be correct. Can't do that, okay? So, at the risk of saying something incorrect, and also like you're just not interpreting the question correctly and you're wasting time. The amplitude is a point on the wave with maximum displacement. Maximum displacement is the amplitude. All right. 1 mark for each of those. We got a beam of red laser light incident normally on a diffraction grating. Diffraction of the light waves occurs at each slit of the grating. The light waves emerging from the slits are coherent. Think what is meant by diffraction. It's another definition, right? So diffraction is just the spreading of a wave as it passes through its boundary. Passes through an opening, like a slit, or around a boundary, like a corner. Spreading of a wave as it passes, through an opening or around a boundary. What is meant by coherence? 2 waves are coherent if they have constant phase difference. Okay. 2 waves are coherent if they have constant phase difference, and the only way that could be true is if they have the same frequency. All right, same frequency. And it doesn't change frequency. That's another sort of thing. Like there are waves that can change in frequency. So if it's a constant sort of oscillation, electric field is oscillating at a constant rate, then the wave frequency will also be constant. But if that changes, the rate of that oscillation changes for whatever reason, then you could have a change in frequency. So like FM radio is a frequency modulated signal. They're modulating the frequency in order to send information via those light waves, radio waves of light. The other way to do it is to modulate the amplitude of the wave, right, which we defined up here. That's another thing you can modulate. So an AM radio wave literally looks like this, okay, where the amplitude of the wave is modulated and the information is sort of contained in these modulations. An FM wave has the same amplitude, but it is the frequency that's modulated. So there's higher frequency or lower. So it's like AM waves look like this, FM waves look like that. It's the frequency that's modulated, information is encoded in the change in frequency. And an AM radio wave, the information is encoded in how the amplitude changes and modulates. It's good to connect, something that's a little bit more unfamiliar and abstract and theoretical with something that we might have a sort of a basis in reality. I'm like, oh, I've listened to FM radio. I know those letters, like I've heard them before. And now we kind of connect that. When we build those connections in our mind, it's a very powerful way to understand and to learn, okay? And I'll sort of, link it back to those essential questions up there above the chalkboard. What do I already know about this topic? How does this topic relate to what we've previously studied? Anytime you can ask yourself those questions, oh, this is exactly the same as this other thing. The history of physics is one where we've simplified things by seeing those connections, by going, the apocryphal story goes, as Newton sat in an apple orchard, an apple fell on his head and the moon was in the evening sky, and he sort of had this epiphany that the same force that makes the moon fall around the earth made that apple fall on my head. And, was able to sort of come up with all of this, theories about gravity. And maybe that's true, and maybe it's not, but it's kind of a nice story. So connecting that and sort of realizing that it's all the same is sort of a rich history of physics and sort of doing that. Remember, I've shared with you the story of James Clerk Maxwell thinking his way through these electric waves that must exist because, electric fields create magnetic fields at right angles, which can in turn create another electric field. And you might have just this electromagnetic wave that could exist. And when he calculated the speed of it theoretically, he realized it was the known speed of light. So saying, oh, that's a simplification. Light isn't a different thing. It's electromagnetic phenomena. It's just like electromagnetism that we've been studying with all these circuits and things that, physicists were experimenting with, in the 1800s and so on. And so that, James Clerk Maxwell, kind of like 1876, I think he published, one of his papers. I don't think it's his equations on electromagnetism, but I actually cited James Clerk Maxwell in my dissertation because he had a really great quote about molecules, about how they have existed since the beginning of time and unchanged. And I like citing something that's a couple of hundred years old. I actually cited St. Augustine in my dissertation. I think that's like the 400s. All right. Easy come, easy go. Let's take a look at the what we're doing with this stuff now, right? So those ideas, that is the foundation, sort of the bottom of the house, the basement, allows us to build up to the structure, the attic, the higher orders of thinking. They tell us the wavelength is 650 nanometers. I guess that's red. The angle between the third order diffraction maxima, that's plural, right? Maxima is a plural. So we got these third order maxima. The angle between them is 68 degrees. Make sure that you understand how to interpret this information and how we define the relevant equation, the variables that are within them. Okay. Like we could anticipate the calculations maybe that we might have to do with this, but let's just read what's happening. Calculate the separation D between the centers of adjacent slits in the gradient. Okay. Calculate is my favorite verb. One of them. Calculate. Great verb. So we need an equation to calculate, and the relevant equation here is going to be theta and lambda. The first thing I would do is remind myself that I'm not given this angle theta here. Rather, I'm given 2 theta. So the third order n equals 3 is 34 degrees away from the 0 order right here. Remember that n is defined relative to this zero order maxima that is directly sort of across from this line of sight. So there's an order here 0, and there must be a 1, 2 order, and I'm told that the third order separate from this third order, because remember there's maxima on either side of the 0. So between these 2, 3 order maxima, the plural maxima is 68 degrees, so it can make sense to you that theta here is 30. Questions about that? We're solving for d, so we just have to, sort of plug in everything like this. D would equal n lambda over sine theta. Substitute in values. 3 is the order. Lambda is 650. Nano is 10 to the negative 9. And we got the sine of 34 degrees to solve it. Calculator check. Got a calculator. We can use it. I mispushed the button. Today might be the day. We can do it. If I get 3.487 by 10 to the negative F6. Let me do a do-over. 3 times 650 times 10 to the negative 9 equals, divided by the sine of 34 degrees. I think that's right. Now I'm getting 3.2. Three times 650 times 10 to the negative 9 equals, divided by now I'm getting 3.487 by 10 to the negative 6. 3.4 by 10 to the negative 6. Let's check our e-learning colleagues. Let's check for their consensus. Yep, they got my answer. Is there further consensus? Yep, that's what we're getting. If you are out there in class or e-learning and you're trying this for yourself and you're getting anything besides 3.4, let's call that 9, let's call it 3.5 by 10 to the negative 6. Okay, now is the time to stop everything and call me over there and we'll figure it out. What are we doing wrong in our calculator that we're not getting it? All right, Trevor, so tell me how you're typing this in. 3.6. Yeah, there's things like that where it's like we're doing an angle, so make sure you're in degrees, okay? The order of 10 here, right? Like this is 6.5 by 10 to the negative 7, so you can put it in that way. So sometimes there's a POT error, power of 10 error, right? I'll kind of write that down here. So if you get this, but it's like off by, it's not this order of 10, then you maybe like, there's something wrong here with the conversion. Be careful about dividing by, certain things, the order of operations, things like that. But yeah, you should get this answer, all right? And if you're not, right, it's important that you figure it out now because you don't want that mistake to keep costing you, marks on page. And again, like, we do a Friday quiz, that doesn't hurt your grades so much, but the goal is to prepare yourself to be successful and not just, the exam at the end of this year, but to physics well enough that you're a somewhat confident physicist making sense of these courses that you're a part of. The more confident of a physicist you can become, the better. Give yourself some units there too. Okay, so let me see if I can just, it almost worked out. Let's slide that over a bit. But meters, okay, so we do need to convert this nanometers down. If you leave it in sort of 650, your answer will come out in nanometers, and then you could convert that. You could convert nano, into meters after if you didn't convert it up here. Like what goes into the calculation comes out of it. It says the red laser light is replaced with blue laser light. State and explain the change, if any, to the angle between the third order diffraction maxima. As we've mentioned before, anytime you're asked to sort of, how is this manipulation going to sort of change some of the output, use the equation to govern your thoughts there. E times theta equals n lambda, we're replacing the lambda, right? The wavelength is shorter. The wavelength is decreasing because red light is the longest wavelength light, blue light is close to the shortest. Shorter visible light is purple. So if this goes down, they're asking us about the angle theta here. All right, so we're not changing D, it's the same diffraction grading, and they're asking us about angle to the third order. So we're not changing that either. The third order maxima. So this was, remember, this angle that they gave us was 68 degrees between these if it's red light. But if we're decreasing the wavelength and everything else stays the same, what has to happen to this angle over on this side of the equation? It's got to decrease too, right? Like this goes down, so this has to go down right along with it because they're both like in the numerator. So we'll state the change to the third order diffraction maxima to the angle is the angle decreases. And then now we'll explain because the wavelength is shorter. Shorter wavelength, lower angle. Okay, they're directly proportional. All right. Thanks for working through that question with us. This has been paper 22 from February, March 2020. We'll see you next time.